This is Lecture 2 in Module 2 of the book Problem-Solving Guide for Electromagnetism and Optics, 3rd edition, utilizing Gauss's law to calculate electric fields. In the first lecture, we had a uniformly charged wire. We wanted to calculate the electric field at distance A away, and we modeled the wire by an infinite number of infinitely small point charges. And we got the little contribution from each one of the charges. We summed them all up, and we got the electric field is directly away from the wire with magnitude 2k lambda over A, where lambda is the linear charge density, so many coulombs per meter, for example. So now we can plug in 2k lambda over A for the electric field at distance A from a wire with a uniform charge density lambda. Let's get the same answer, hopefully, by using Gauss's law. Instead of summing over an infinite number of infinitely small point charges, let's use Gauss's law. Gauss's law is E dot A is 4 pi k q enclosed. We're going to dot the electric field vector with the area vector, and that's 4 pi k q enclosed. The area of what? Well, you have to choose a Gaussian surface. This equation is challenging to understand, but it's the only equation in Module 2, so we're going to devote a lot of time to it. The first thing we have to do is define a Gaussian surface that encloses a volume, a closed surface. The key to using it effectively is to select an appropriate Gaussian surface, one that makes your life easier. The left-hand side of Gauss's law is this dot product. This is the hard part. This is the easy part over here. The right-hand side is pretty easy. This is the hard part. We have to choose a surface that makes this equation useful. Gauss's law is always right. It's not wrong. It's just useful or not useful. And we want to make it as useful as possible. An ideal Gaussian surface will have the E and A vectors either parallel or perpendicular. We want the electric field vector to be either along the surface or parallel to the surface, penetrating at a right angle or not penetrating at all. If the E and A vectors are parallel, E dot A is simply E times A. If the E is perpendicular to the surface, the E and A vectors are parallel because A vector is perpendicular to the surface, directly outgoing from the surface. If the E and A vectors are perpendicular, which means that E is not penetrating the surface, then E dot A is 0. So we want to choose a surface so that E dot A is either E times A or 0. So there's our wire. Since we want the surface to be perpendicular or parallel to the electric field lines, it's important to be able to picture what the field lines look like. The field lines are going away from the wire in all directions. It's hard to see that in this view, but if we look down the wire, if we look down the axis of the wire, if we rotate the wire so it's pointing directly into and out of the page, we can see the field lines directly away from the wire. I can draw them up here and down here, but really they look like this. We want a surface that hits the field lines at a right angle all the way around, perpendicular or parallel to the surface. A surface that will do exactly that is a cylinder, a radius A, whose major axis is along the wire. We're going to surround the wire with a cylinder of radius A, some imaginary Gaussian surface, and here it is. And I'm going to put it on the bottom figure too, because that's what we can see. There's our Gaussian surface. We're looking right down the cylinder. The field lines are penetrating the curved surface at a right angle all the way around, which is what we want. The cylinder basically is two different surfaces, a curved surface, and there's the ends. The two flat circles on the ends. The field lines are perpendicular to the curved surface. We can see that right here. That's a right angle all the way around. The field lines aren't penetrating the ends at all. The field lines are along the ends. There's no puncture of the two circles by the field lines. With a curved surface hitting at a right angle, the E vector is parallel to the A vector, so it's just E times A. For the circular end caps, E dot A is 0. E is not penetrating the circular end caps at all. The area of a curved surface of a cylinder is 2 pi RL, and it's easy to see why this is if you unroll the cylinder. The circumference of this circle is 2 pi r, and if you unroll it flat, the length is 2 pi r, and this is L, so length times width. This, you're unrolling it into a rectangle. One side is 2 pi r, the other side is L. The area is 2 pi RL. The left-hand side of the Gauss's law equation is now E times A, and A is 2 pi RL. We don't include the circles at the ends because the field's not penetrating the circles. Now we can think about the right-hand side. 4 pi K Q enclosed. Q enclosed is the charge inside the surface. So the surface encloses a volume. We want to take an inventory. What charge is inside our Gaussian surface? Well, it's the charge that's on the wire inside the Gaussian surface. That's it. We don't have the whole wire. We have a part of the wire. But we can just go ahead. E times A, 4 pi K Q enclosed. We can solve for E. We can get the electric field at A. The radius of the cylinder is A. This R is the radius of the cylinder. Remember, it's 2 pi R L is the area. We can plug that in. Now we can solve for A. Divide both sides by 2 pi A L. And the 4 and the 2 give it 2. The pi's go away. And we get 2K over A times this term, Q enclosed, over the length of the Gaussian surface. Q enclosed over the length is the charge density, charge per unit length. And we define that as lambda. So now our equation is 2K lambda over A. And that's the equation we got before using integral calculus by summing over an infinite number of infinitely small point charges. That's how Gauss's law is applied to the charged wire. Now let's consider a charged disk. The charged disk has radius r, charge big Q. What is the magnitude of the electric field directly above the center, very close to the plate? Big plate, thin plate, total charge plus Q, radius r. Let's start with a good diagram. There's a plate. It's not so thin, but at least you can see it's a plate. We want another field right in the middle, a little teeny distance above the center. If it's a positive charge, the field lines will be directly away from it. So there's some field lines. There are field lines over here that curve away, but we're in the middle. We're not going to worry about those. A good Gaussian surface is a cylindrical glove that just fits over the Gaussian surface. We want another field just above the surface, so we're going to put a Gaussian surface right there. So there's our Gaussian surface. In the previous problem we did with the wire, we had a cylindrical Gaussian surface as well. But this Gaussian surface is a flat cylinder. In this problem, the field lines are going through the circles. They're going through the flat ends. There are some field lines going through this curve. If I put a positive charge over here, it would certainly go that way, away from the plate, if the plate was positively charged. But the plate's thin. It said in the problem that the plate was thin. Here I didn't draw the plate so thin. So this curved area is actually much smaller than depicted here. So we could ignore that. So now we can apply Gauss's law. E dot A is 4 pi k q enclosed. E is what we want, that's our unknown right here. The area is pi r squared for the top and pi r squared for the bottom. The field lines are going through the top half of the cylinder and the bottom. So it's 2 pi r squareds. Over here we have 4 pi k q enclosed. We just solve for E. What is this q enclosed? Well, our Gaussian surface encloses the whole plate. We have the whole plate inside of it. And it was given that the plate has a big charge, capital Q. So we just substitute in capital Q for the charge enclosed. So now we have the electric field a small distance above a circular plate of charge big Q. You have to be really careful here, because this R looks like the distance away from a point charge, but this R has nothing to do with the distance away from the plate. This R is the radius of the plate. The field close to the plate is constant. The field lines are not going away from each other. They're parallel. If you go up far distant, these lines will start to spread out, which is why we have to ask, what's the field close to the plate? Those are a couple examples of Gauss's law. You should now start doing a lot of problems.